Okay, so welcome back to this next video in which we are discussing experimental methods for investigating exocytosis. Okay, so we are in the process of discussing how we can measure capacitance changes as a measure for exocytosis. So we're just discussing what membrane capacitance actually is. So basically, membrane capacitance is all about how much charge you have to move across a cell membrane in order to produce a certain change in voltage. Okay, so if you want to produce a certain change in voltage, for instance, negative 65 millivolts, you have to times it by this capacitance, which is just some constant for this cell membrane here, and that will give you how much charge you have to move from the intracellular compartment to the extracellular compartment in the form of these potassium ions in order to actually produce that change in electrical potential difference across the cell membrane. So what does capacitance actually depend on then? Okay, well, let me give you some motivation for this. If we have a tiny little cell here and a massive great cell here, okay, and we want to produce the same electrical potential difference across their cell membranes of negative 65 millivolts, which one do you think you're going to have to move more charge across the membrane in order to make that electrical potential difference across the cell membrane? Okay, well, evidently it's going to be the bigger cell. Of course you're going to have to move much more potassium across the cell membrane if you're going to produce the same electrical potential difference across the bigger cell membrane as you want to produce across this tiny little cell membrane. So basically, one of the key things that capacitance depends on, okay, is proportional to, in fact, is the surface area of the cell. It completely depends on the surface area of the cell. And in fact, if you double the surface area of the cell, you double the capacitance of the cell. You double how much charge you're going to have to move across the cell membrane in order to get the same change in electrical potential difference across that cell membrane. And this is the key thing that we are going to use here. The fact that if you increase the surface area, you increase the capacitance of the cell membrane. Okay, so basically when you exocytose a vesicle, so let's have a look at this in the axon terminal here. Let's say this is our synaptic vesicle here. When that fuses with the cell membrane, you have actually increased the surface area of the cell membrane. So you should change the capacitance by a tiny little amount whenever you exocytose a synaptic vesicle. So that's how we could work out that you have exocytosed a synaptic vesicle by measuring a change in membrane capacitance. So how do you measure membrane capacitance? How do you work out this number? Well, the actual technicalities of doing it are far more complex than what I'm going to tell you. Okay, I'm going to give you the basic raw idea behind how you measure membrane capacitance. So basically, capacitance is all about how much charge you have to move in order to produce a certain change in voltage. So quite simply, if we've got a cell here and we want to measure what the capacitance of the cell membrane is, all we need to do is change its voltage across its cell membrane and see how much charge we have to move in order to actually produce that change in voltage. Okay, so normally the electrical potential difference across the cell membrane is negative 65 millivolts. Let's say we want to step that up to negative 40 millivolts. Okay, so we want to produce a change in the electrical potential difference across the cell membrane. Now to do that, what are we going to have to do? Effectively, we're going to have to move negative charge out of the cell, basically. Okay, so we're going to have to move negative charge from the intracellular compartment to the extracellular compartment. Why? Because when you move negative charge out of the intracellular compartment, that's going to raise the electrical potential intracellularly, so this number's going to now go up a little bit. Okay, when you move it into the extracellular compartment, you're going to decrease the electrical potential extracellularly, so this number is going to go down a bit. So you can see that these two are going to be coming closer together, and therefore the amount that you step down is going to be decreased. Okay, then of course the question is how much negative electrical charge are we going to have to move to produce this change in electrical potential difference across the cell of 25 millivolts we want to change it by. Okay, well that's going to depend on the capacitance. So basically what we do is we use experimental kit to force the electrical potential difference across this cell membrane up to negative 40 millivolts. Now there are mechanisms for doing that. They're known as voltage clamps. Okay, so we're going to use a voltage clamp to artificially change the electrical potential difference across the cell membrane from negative 65 to negative 40 millivolts. And then we can just ask the voltage clamp, how much negative charge did you have to move from the intracellular compartment to the extracellular compartment to actually produce that change in electrical potential difference of 25 millivolts? Okay, and then we can work out from that what the capacitance must have been, because we know what the change in electrical potential difference we wanted to produce is. The voltage clamp gives us how much charge it moved. It will tell us how much current actually moved, okay, which will be how many electrons it moved effectively from the intracellular compartment to the extracellular compartment, okay. And then we can just work out the capacitance by effectively just rearranging this equation to capacitance is equal to change in charge, the amount of charge you moved, divided by how much the voltage changed. Okay, and that's then how we can measure membrane capacitance. Now, in reality, it's far more complicated than that, okay, because you can't just instantaneously step up the electrical potential difference from negative 65 to negative 40 millivolts. And as soon as you change the electrical potential difference from the resting membrane potential to something else, suddenly you're going to have net movements of charge across the cell membrane through ion channels, okay, and that complicates the matter. So remember, at resting membrane potential, the key thing is that you have no net movement of charge across the cell membrane. Yes, you're getting potassium ions moving out of the cell through potassium channels, but you're also getting sodium ions moving into the cell, and those completely balance each other, okay, so that there is no net movement of charge across the cell membrane. As soon as you deviate the electrical potential difference away from resting membrane potential, then you destroy this equilibrium, and you're going to start getting net movements of charge across the cell membrane, which will oppose your movement towards negative 40 millivolts. They will try to take it back down to negative 65 millivolts. Okay, so that makes it far more complicated, and it makes this a job for calculus, okay, but at fear of losing my audience, we're not going to go there, but that's the basic idea of what you do. You change the electrical potential difference and you ask how much charge does that have to move, but in reality you're going to have to move far more charge than you would actually have to move if this was the only force you were against, because, as I say, as soon as you deviate from resting membrane potential, this is going to be working against you, which means you're going to have to redouble your efforts here. Okay, so it becomes a nightmare basically, and to do it you need more advanced maths than this equation. Okay, right. But that's the basic idea, that you can measure capacitance across the cell membrane by making changes in the voltage artificially across the cell membrane. Okay, so what you can do is you can continuously measure the capacitance across the cell membrane of these axon terminals or across the cell membrane of an adrenal chromaffin cell, and then if you see the capacitance suddenly go up, that suggests that a vesicle has exocytosed and added its surface area into the plasma membrane surface area. Okay, right, next up, the final technique that I want to discuss is a technique known as amperometry. Okay, and this basically is a way that you can measure the amount of neurotransmitter that has been released from an axon terminal. Okay, so let me draw the axon terminal here. So basically this works with certain neurotransmitters, okay, so it works for the catecholamines basically, noradrenaline, dopamine, and adrenaline. Okay, so let me show you the structure that all of these neurotransmitters have in common. Okay, so the thing that they all have in common is that they have a catechol ring, and this is the essential thing for this amperometry reaction that we're going to discuss. So let me show you what a catechol ring actually is. So a catechol ring is basically a benzene ring, so I'll draw a benzene ring here. So it has alternating double and single bonds. This is it drawn with the Kekule structure in skeletal form. So you have a 6-membered carbon ring where you have alternating double and single bonds, and then each of the carbons will have a hydrogen coming off. Now in the case of catechol, 2 of these carbons are going to have lost their hydrogens and are instead going to have alcohol groups coming off. Okay, so this is the structure of the catechol ring. Okay, right. Now, noradrenaline, dopamine, and adrenaline are all going to contain a catechol ring. In fact, they're just going to have an R group effectively off here that will vary for the 3 different neurotransmitters. So let me show you the structure of that R group in the case of these 3 different neurotransmitters. So we'll start off with dopamine, DA here. So the neurotransmitter dopamine has effectively just an ethylene group, 2 methylene groups joined together, and then it has an amino group on the end here. Okay, so this is the R group of the neurotransmitter dopamine. So just translate that onto there, and then you've got the neurotransmitter dopamine. Okay, or DA for short. Okay, noradrenaline is then just a little modification of dopamine rather. Okay, so all you do is stick an alcohol group onto this carbon effectively here, and then you leave everything else the same. Okay, so very much so related to dopamine. So this is noradrenaline, which I've abbreviated to NA, also called norepinephrine if you're in the States. Okay, right. Then the final catecholamine is adrenaline, and adrenaline is basically just a modification of noradrenaline now. Okay, so draw out the structure of noradrenaline, and then what you're going to do is stick a methyl group onto this amino group like so. Okay, and that now gives you the structure of adrenaline, also called epinephrine. Okay, right, so those are the 3 catecholamine neurotransmitters as they're called, and they're called that because they have a catechol ring, and then they also all have an amine group. Okay, so dopamine has an amine group, noradrenaline has an amine group, adrenaline has an amine group. Okay, hence catecholamine. Okay, right. Now, the key thing here is that these can be induced to undergo an oxidation reaction by the presence of an anode. So let me show you what you're going to do. Basically, you're going to take your catecholaminergic neuron, which is releasing one of these neurotransmitters, or potentially more than one of them, okay? And basically, you're going to put a tiny little electrode here, a tiny little electrode known as a microelectrode. Okay, this is usually made out of carbon fibers, so you'll often see the terminology carbon fiber microelectrode. Okay, so a tiny little electrode, and basically this is a positively charged electrode. Okay, so the fancy word for a positively charged electrode is an anode. Now, what's the key thing to understand about positively charged electrodes? They're effectively vacuum cleaners. Okay, they suck up electrons, they suck up things with negative charge. Okay, so if you've got negative charge, you're going to get sucked up this thing, and off you go, off you whiz. Okay, so it's effectively like a vacuum cleaner for electrons. Now, basically, when you secrete your catecholaminergic neurotransmitter, okay, and I'll just draw out the catechol ring now with the R group. Okay, so once again, here is the catechol ring, the alternating double and single bonds, the alcohol groups here. Basically, this molecule can be forced to undergo a reaction which produces electrons, so that those electrons can be sucked up by this anode, basically. Now, when something undergoes a reaction where it loses electrons, that's known as an oxidation reaction. So basically, the anode can induce oxidation reactions. It can induce reactions which give up electrons, basically, so that this anode can whiz off with the electrons. Okay, right. So what happens to the catechol ring then? Well, basically, you're going to break this second of the 2 bonds in that double bond there. So you're going to break the benzene structure. Okay. You're also going to break the bonds between the oxygen and the hydrogens in these alcohol groups. Now imagine just for the purposes of understanding this reaction, and this is not supposed to be an electronic flow diagram whatsoever, okay, but just for the purposes of understanding this reaction, imagine giving one electron in each of these bonds that we've broken back to each constituent of the bond. So for instance, in this bond here, imagine giving one electron back to this carbon and one back to this carbon. In these bonds, give one electron back to the oxygen, one to the hydrogen. Okay, that then leaves this oxygen with a free electron, this carbon with a free electron, and this oxygen here with a free electron, and this carbon here with a free electron. So what they're actually going to do is react, okay, in those pairs that I just outlined. Okay, so you're going to get these carbons forming double bonds with those oxygens, basically like so. And you've still got your double bonds here. Okay, now what does that then produce? Well, it produces two hydrogen atoms. Okay, and two hydrogen atoms consist of two protons and two electrons. Now what's going to happen is the two electrons are going to whiz off up the anode. The two protons aren't going to whiz up off the anode. They can't go anywhere near the anode. They're going to go into free solution. Okay, so they're just going, you're effectively producing free protons, which is just acid basically. Okay, so the electrons are taken by the anode, the protons are just thrown off into free solution. And how many electrons is this anode actually going to produce? Well, that will be determined by how much neurotransmitter you release. If you release loads of neurotransmitter molecules, the anode is going to get loads of electrons. So by measuring the current that you're going to get, okay, i.e. how many electrons you're getting flowing through this, you can then get a measurement of how much neurotransmitter. So by looking at the current, you can assess how much neurotransmitter has been released by your axon terminal, and hence that's a way of measuring the amount of neurotransmitter that has been released. Okay, and that's also a very useful tool for studying exocytosis.